Hello viewers, I am Kausalya. Today we are going to have an introduction about signal flow graph. So a signal flow graph is nothing but this is again used to find the transfer function of the system. So as we all know, the transfer function is nothing but Laplace transform of output to the Laplace transform of input. And now we are going to discuss about terms used in signal flow graph. So this is a typical representation of a signal flow graph. With this diagram, I will explain each and every term, then it will be easy for you to understand. Right. So the first one is node. So here node is nothing but, you see here I had written right 1, 2, 3, 4, 5, 6, 7, 8. These are said to be nodes. So a node is nothing but it is a point representing a signal or a variable. So this is a node is nothing but it is just a point which is used to represent a signal. Right. So here the above graph has 8 nodes. Right. The next one is branch. So a branch is nothing but, you see here I am having two nodes, right, 1 and 2, and these two nodes are connected by a line segment, right, and this line segment is known as branch. That's all. So it is a directed line segment joining two nodes. Okay, but it is a line which joins two nodes. That's it, and that branch will be having some direction, whether from 1 to 2 or from 2 to 1. That's all. Right? The third one is transmittance. So here the transmittance is nothing but, as we say, here this is your node 1 and this is your node 2. So what is the gain which is acquired by the signal when it flows from when it travels from one node to another node? That is, a signal moves from node 1 to node 2. During the travel time, it gains, okay, it gains something. That gain is known as transmittance. So in this branch, the gain is nothing but G2, right? Then the next one is input node or source node. So here, the input node or source, it has only outgoing branches because this is the source, right? For example, here consider a node A. And this node A is the source, and from the source there will be only outgoing branches, right? Then the next one is output node or sink. Sink, as we all know, this is a point where it receives all the outcomes, right? So it has only incoming branches. Here B is the example for the output node. Since you see in B, it receives signals, right? Only signals come towards B. Whereas in the case of A, the signals flows outward from A. So A is known as source and B is known as sink. And the next one is mixed node. So here, let C be the node present here. When you observe carefully, this C has both incoming as well as outgoing branches. So when you listen, these two are the incoming branches and this one is the outgoing branches. And it is known as mixed node because it has both incoming as well as outgoing branches. Right. Then the next topic is path. So here a path is nothing but, this is an example, that is, a signal starts from node 1 and it travels through node 2, node 3 and finally it reaches node 4. That is, it is a path through which your signal travels. That's all. Right. So a path should not cross a node more than once. So this is a path, and through this path a node should be crossed only once. You see here node 2 is crossed, right? Then again there is no node 2, only some other nodes are present here. So a node should be crossed only once in a path, right? Again the path will have arrowheads to indicate whether the signal flows from which node to which node. That's all. And the next one is open path. Here open path is nothing but it starts at some node and it ends at some other node. right? This is an open path because it starts at node 1 and it ends at node 4. So this is an open path, right? And the next one is closed path. So here in this case, closed path, it starts at one node and it travels through some nodes and again it returns back to the node where it gets started. So here in this example, the signal starts at node A. It travels through B and C and finally again it reaches node A. So on the path traveled by the signal is known as the closed path. That is, it starts and ends at the same node, right? So this is our closed path. And the next one is forward path. So here the forward path is one. That is, it is a path from input node to output node that does not cross any node more than once. Again, it is similar to that of our open path here. That is, it goes only forward. Can you people understand? That is, it just starts at node 1. It travels through some other node. It goes on. That is, it travels only in the forward path. That is, no reverse direction. You see here, all the arrowheads goes in the forward path. So this is known as a forward path. And the next one is forward path gain. So what is meant by forward path gain here? It is nothing but product of the branch transmittances of the forward path. As I already said, transmittance is nothing but it is the gain obtained by the signal when it moves from one node to another node, right? So here you see, let this be node 1, 2, 3 and 4. So the gain obtained by the signal when it moves from node 1 to node 4 will be, just you have to multiply the gain, G1 into G2 into G3, and hence as this is a forward path, we are naming it as forward path gain, right? And the next one is individual loop. So here individual loop is nothing but, again you see, a loop always represents a closed path. Hope you people are clear with this. That is, it starts at node 1, it passes through node 2, node 3 and finally it reaches node 1. Again, so this is a closed path and this is known as individual loop. That is, it starts at some node 1, it travels through some distance and it again reaches the same node 1. Okay, this is an individual loop. And again, when you consider individual loop gain, just you have to add the gain in each part. Here, from 1 to 2, the gain is G2. From 2 to 3, the gain is G3. And again, from 3 to 1, the gain is H1. So, just you have to multiply. G2, G3, H1 is nothing but your individual loop gain. And the next one is, this is your last one, that is non-touching loops. So here non-touching loops are nothing but, consider a path, okay, but this is a path and here we are having some nodes. Let us say from 1 to 5. So here this is one loop, right? It starts at node 1, it travels through node 2 and again it reaches node 1. So this is a closed path, so this is loop 1 and again this is your loop 2. It starts at node 4, travels through 5 and again reaches 4. So here when you keenly observe, these two loops are individual loops or non-touching loops. That is, this loop is separate and this loop is separate. Again this loop has nodes 1 and 2 and this loop 2 has nodes 4 and 5. So there are no common nodes. So when you have loops which don't have any common node are known as non-touching loops, right? And the next one is the most important topic, that is Mason's gain formula. So here when you look at Mason's gain formula, so this is similar to that of your transfer function. So how we write transfer function generally? It is nothing but Laplace transform of output to the Laplace transform of input. So generally output are denoted as C of S and input are denoted as R of S. Right, this is a general formula. But when you come here for a signal flow graph, the overall gain, it is nothing but the transfer function, right? So it is given as 1 by del summation of k, pk into del k. So here t, as I already said, t is nothing but the transfer function of the system. And what is meant by pk? Pk is nothing but forward path gain of kth forward path. Because whenever a problem is given, we don't know how many forward path will the graph will be having, right? It depends, it varies according to the type of problem. So here there may be 2 forward path, there may be 3 forward path, or whatever may be. Sometimes in case there may be only 1 forward path. So pk is nothing but forward path gain. Gain is nothing but you have to multiply all the gains which are present in that forward path. So pk is forward path gain of kth forward path, right? Then del. So here del is nothing but, this is a formula, 1 minus sum of individual loop gain. So here you have to find individual loop and it gains, plus sum of gain products of all possible combination of two non-touching loops. Okay, you have to find the gain product of two non-touching loops if possible. If it is given, if it is available in the problem, you can calculate this gain product of two non-touching loops. And the third one is again sum of gain product of all possible combination of three non-touching loops. Suppose if the given signal flow graph has three non-touching loops, then you can find the gain product. Right, this seems to be quite confusing, but whenever we enter in solving problem, it will be quite easier. Right, I will explain you while solving problems. And the last one is del k. Del k is nothing but del for that part of the graph which is not touching the kth forward path. So we have to again find the del. What is the formula for del? This is the formula for del. If you have any part, okay, any part of the graph which is not touching the forward path, then you have to calculate the del for that part of the graph. Here, that's all. Hope you people understand. Thank you.